Section 9.4, mathematical induction. So this is kind of the first section that has to do with mathematical proofs. So for those of you that are going to be either something in the mathematical sciences or something in the sciences or engineering or anything like that, there's a point in math where you kind of stop solving problems and then you start proving theorems instead. So after like calculus 3 and linear algebra, things like that, which are usually taken like in your later half of your bachelor's degree. After that, the classes become kind of just arguments and proofs. It's not about solving problems anymore, okay? So this is kind of an intro to that sort of idea, but only focusing on one thing here. In this case, counting and series and sequences. So let's start with example 2. And this is how we use induction to prove something. So they're asking us here to prove this sum, S sub n, is equal to 1 plus 3 plus 5 plus 7 plus ... The next number is given by this formula, 2n minus 1. So the 2n is an even number, right? Because it's multiplied by 2, and then you subtract 1 to give you an odd number. So essentially what they're saying is that's how you get the next term, right? So for example, remember n is a integer, a positive integer. So when n is 1, think about it, we plug it into that 2n minus 1. So when n is 1, that's 2 times 1 is 2, minus 1 is 1, right? And that's how you get that first value. When n is 2 in this sum, that's 2 times 2 minus 1, so that's 4 minus 1, and that's how you get 3, and so on, right? So each one of these represents a different n. And goes on from there, right? So if you want the next number, you plug in n minus 5, n minus 6, n minus 7, and so on. So what they're saying here is this sum, no matter where I stop, is the same as taking n, so n is the number of terms you have, right? And squaring it. Okay, so for example, let's say I do up to 7, right? So up to 7 is only an n of 4. So S sub 4 would be equal to 1 plus 3 plus 5 plus 7. And what would that sum be? So in that case, it's only 4 numbers, so it's easy for us to compute. It would just be 1 and 3 is 4, and then 4 and 5 is 9, and then 9 and 7 is 16, right? So is it true that the sum is equal to n squared? Well, if I only go up to 7, that means n is 4. And if I plug in 4 over there for the n squared, I get 4 squared is 16. Does that make sense? So it does match up, right? If I do just 2 n's, the first 2 terms, n is 2, the sum would be 2 squared, so that's 4. Is it? 1 plus 3 is 4, so that checks out. Does that make sense? So, you can check all these, right? But what would it take for us to prove that this is going to work all the time? That's the question, right? Okay? Because we know we can see it works for 1, right? 1 squared is 1. We can see it works for n equals 2. We get a sum of 4. 3, we get a sum of 9. 4, we get a sum of 16. And we can kind of see maybe a few more, right? But then what about when we get to 36 terms or 150 terms, or what about 1,000,000 terms? How are we going to check those? Does that make sense? So what we can do is prove that this is going to work all the time. And the way we do that is with induction. So induction proves something for what you see and then plus one more, right? So plus one more means that it goes on forever. So this is how it's going to work. First of all, let me put here. This is for all n's that are greater than or equal to 1, right? So obviously n cannot be -2 or something like that. We start with 1 and then 2, 3, 4, and it goes from there. So this is how we'll start the induction process. And let me do this example and then I'll show you the official sort of definition of induction that they have here. There's two main parts to this. The first part is going to be, we're going to show that the formula is true when n is equal to 1, okay? So part 1, we're going to show that is true for, actually let me put s sub n first, for n equals 1. So this is always going to be the case. We're going to do it for n equals 1, right? So think about that. If n is 1, that means this is going to be s sub 1, right? And this is going to be 1 squared. Now we treat these separately, right, as two separate sides and see if they're equal. So if we have s sub 1, that's going to be just the number 1, right? Just the first term. So that's just going to be a 1. And 1 squared is also just a 1. Does that make sense? So here we have shown that it does work for that case, right? For the case where n is equal to 1. So first we show the first case works. They call it the base case sometimes. So we're showing the base case works. And what this is doing is it's setting up our proof. So this is a good way to start because we're showing that it works for n equals 1. And now in the second part, we're going to show that it works for, think of it as n plus 1. So whatever n is plus 1. So if we show that it works for the next one, then that means it works forever, right? Because then part 1 could be a 5, so n plus 1 would be 6. And part 1 could be a million, so n plus 1 would be a million and 1, right? So think of it that way. So it goes on forever and ever. So part 1, that's it. That's all you have to do is check the base case. And then we move on to part 2. And this is how you'll do all of them. Part 1 and part 2. So we're going to start with the statement that we were given, which is the S sub n statement with the formula. We're going to assume that that is true. But we're going to use, let's use a different variable than n. Let's use k. So we're going to say, let's assume that sk is true. And show means also prove. Show that s sub k plus 1 is true. Okay, so this is going to be the basis of all your induction proofs. So we're going to assume that s sub k is true automatically. And then we're going to show that s sub k plus 1 is true. So the first part is the given part, right? That's our assumption. We're going to assume that s of k is true. So we're saying that s of k, let's put assume, s of k. So it's just the s sub n statement, but with k's instead of n's. So this is equal to this, right? Plus, keeps on going, 2k minus 1. And we're saying that this is equal to k squared. So it's just what we were given, right, in the beginning, but with k's instead of n's. So we're going to assume that this is true now. This part at least. Okay, and then after this, we're going to do, it's like a subpart to this. Now, we show that S sub k plus 1 is true. And what is that going to look like? So S sub k plus 1 would be 1 plus 3 plus 5 plus 7 plus all the way up to here, up to whatever that term is, right? But we're going to add an additional term here. So if our original sum goes up to, let's say, 19, then what is it like when it goes up the next term, right? 21, since we're adding odd numbers here. So if we're doing a k of 17, right? What about a k of 18? Or we're doing a k of 1,000,000, what about a k of 1,000,001? So since this is our last term here, here I'm going to add, the next term would be k plus 1 instead of k. So it's 2 times k minus 1 plus the next term should be 2 times k plus 1 minus 1. And this is equal to, from above, we know that this is k squared. And we know this part is k squared because this is equal to this, right? So notice I have this here, like that, but I have that extra term. So then I want to show that this is also equal to adding that term. Once I add it to one side, I have to add it to the other side. How should we do this? Let's do this with yeah, let's add it together. Okay, so then I'm going to add the same thing. That. Let's try it this way. So this is what's being, that's new, right? This is my next term. So wherever it is that this leaves off, this is just adding one more term. But of course, if we add something to the left side of an equation, we have to add it to the right side, right? Now, in order to show that, or to prove that this is going to work for all n's, right? All k's. What we're going to do now is work with that right side. Work with this right side and see if we can get something that kind of looks like this, but it'll be one higher. Okay. So first, let's expand this on the right side, which is k squared plus I got a 2 times k, 2 times 1 plus 2 times 1 minus 1, which is k squared plus 2k plus 1. And if I factor this, I would get k plus 1 squared. Okay, and the fact that this is one higher than this than this one, the original one. This shows that this will work for any number, right? Any k or any n. So once you prove the base case, then this shows that the next one will work. And from there, it's sort of like this is what they call the induction step. So this proves that then the next one will work after that, the next one will work after that, the next one will work after that. So that's a formula that we can always use, right? When you're adding odd numbers, you can add the first million odd numbers or the first trillion odd numbers, or however many you have, just by squaring the number of odd numbers that you have. Okay. So one thing that people will do sometimes is here at this step, they'll look at what they have here on the right side, and they'll kind of make a note, right? Our goal is to have what you see, one more up. So k squared would become k plus 1 squared. But then we have to show that we can get there algebraically. So it's kind of one of those situations where you know what you're supposed to end up with before you get there. Let me show you what the book has, which is 9.4. Okay. So they're using P here. So let P be some statement. Our statement was S, involving the positive integer n. And there you see the two main steps. So if the base case is true, so first you must check that the base case is true. If the base case doesn't work out, then that means you can't do this. All right. So the base case has to be true, just like we did in part 1. And then number 2, for every positive integer k, the truth of p sub k implies the truth of p sub k plus 1. Then the statement p sub n must be true for all positive integers. Okay, so that's how you say it in a math language. Let's try example. Yeah, let's do 3. So same process, different statement. This is S sub n is equal to, so this sum, 1 squared plus 2 squared plus 3 squared plus 4 squared. All the way to some, whatever n you stop at, right, squared. The actual computation of this, right, the actual answer to this is given by the formula n times n plus 1 times 2n plus 1 over 6. Base case, we're going to check if S sub 1 is given by the formula. Looks something like that. Now S sub 1 is just the first term, right? What we get from the first n equals 1. So it's just 1 squared, so 1 squared is just 1. So S sub 1 will be 1. And on the right side, we just worked that out. So we got 3 times 2 times 1 is 6, and then divided by 6, we get 1. So the base case checks out, right? So then that means we can go to part 2. All right, so part 2 is we assume that S sub k is true, and then we show that S sub k plus 1 is true. So we'll assume that S sub k would be this, so this statement, this sum, all the way to sum k squared is equal to k times k plus 1 times 2k plus 1 all over 6. So by assume, we're saying we believe this is true. But we're going to show that it's true for k plus 1, right? So adding one more term. So this would be the same statement. Up to here, right? But then we add one more term, so if k squared is the last term, the next term for after that would be k plus 1 squared. And we can rewrite what we have up there. And then we added this extra piece to it, right? So this part is that comes from our assumption, right? We're assuming that stuff in purple is equal to that side in purple. And then we're adding this extra term to see if it's true for the next step, right? So we want to get our goal, you can tell from this one, right? From our assumption. So our goal is to get once we work on this right side, we want to get something that says like, instead of k, it would be k plus 1. Instead of k plus 1, this would be k plus 2. Does that make sense? Or think of it as k plus 1 plus 1. And this would be 2 times k plus 1 plus 1. Does that make sense? So this will be a little tricky because the 2 will distribute to the k plus 1. Right? So we'll see what we end up with. N over 6. Since the 6 doesn't have any k, so that comes along for the right. All right, let's work on this right side. What would be better? Should we get the same denominator? So let's say we do a denominator of 6 on that term I added. So that means I would get k times k plus 1 times 2k plus 1 plus, and then to get a denominator of 6 on that term in light blue, I would have to multiply it by 6 over 6. So it would look something like this. Yeah.
Why did you put the 6 times
Which one? This one? Because this one doesn't have a 6 on the bottom. So if I put a 6 here, I have to take it out by putting it up here. So if you think about it, this is 6 divided by 6, so it's still just k plus 1 squared. And I'm trying to do it this way just because if you notice that left side has a k plus 1, this left part, and this has a k plus 1, so I'm hoping we can factor that out and then continue from there. Because if I start multiplying all this out, I'm going to get k, that's going to be k cubed, right? Plus some k squareds, and then it's going to be order 3, right? A polynomial, and those are kind of harder to factor out. So let's see if we can kind of separate it before that gets to that point. So everything's over 6, right? So let's take out the k plus 1 here. If I take this out like that, let's do this. For the left side, I would end up with just k and 2k plus 1. And then over here, I would have plus 6 and then a single k plus 1. Does that make sense so far? So k plus 1, we can take one of them out. Okay? K plus 1 times this and this gives me this part. And then over here, it's 2 of them, right? So k plus 1 times k plus 1 gives me k plus 1 squared. And of course, the 6 just goes along. Inside those brackets, we can start putting that together because it looks like it's only going to be a quadratic at worst. So quadratics we can deal with pretty easily. So let's multiply that out. That would be 2k squared plus k. That's that. And then we'll do 6k plus 6k plus 6. We end up with 2k squared plus 7k plus 6. Okay, and let's see if we can factor this. The 2k squared plus 7k plus 6. So 2k and 1k. That's 2k squared. And then we need to get a 6, right? So that's going to be either 6, 1 or 3, 2 in some combination with these. So let's try. If I do 3, 2, that's going to be 6k's and 2k's. It does not give me 7. So what about 2, 3? 2, 3. That's 4k in the middle and then 3k on the outside. So that does give us 7, right? If I do plus and plus. And if you notice, that is pretty much what we need. Because we need a k plus 1. We need a k plus 2. And then this would be a k. Do this in a different color here. Our goal would be k would become k plus 1, k plus 1 would become k plus 2, And then the 2k plus 1 would become 2 times k plus 1 plus 1. And it's all over 6, right? So this would mean, if I simplify a bit, this one, this term, and this would be what? 2k plus 2 plus 1. So this would be 2k plus 3, all over 6. So that is where we're at now. Okay. So the real work is really this part, right? Just showing that you can go from the term that the extra term you added to our goal. And our goal you'll be able to see from the beginning, right? Before you even start doing this. Any questions so far? All right, let's try one that looks a little different. This is proving not a sum, but a property. Let's jump to example 5. We'll come back to 4. Prove that 3 is a factor of 4 to the n power minus 1. So basically, we're going to try to prove that n can be any positive integer, right? So whatever n is, if I plug it in as a power of 4 and subtract 1, we're saying that that number is going to be divisible by 3, whatever that number might be. And remember, with induction, n is always a positive integer. So let's start with the base case, which is the easiest step. Part 1, or sometimes they call it step 1. For n equals 1, we would have 4 to the 1 minus 1 would be 4 minus 1, which is 3. This is true, right? Because 3 is a factor of 3. Since I can write 3 as 3 times 1, that means it has 3 as a factor, right? So 3 is a factor of 3, 3 is a factor of 6, for example, 3 is a factor of 9, 3 is a factor of 12, and so on. So the base case works. We can move on to part 2. So we will assume that it works for the statement n equals k, and then we'll prove that it works for k plus 1, right? So let's assume three is a factor of 4k minus 1. But we are going to show is a factor of 4 to the k plus 1 minus 1. Okay. Now here, basically, we're going to sort of manipulate that expression and try to show in some way that it is divisible by 3. Where to start? So we want to try to get this in a more, write it in a more factorable way. And also we're going to try to squeeze a 3 out of this expression, factor of 3. So the trick they use for this one is they take our expression, right? 4 to the k plus 1 minus 1 is equal to 4 to the k plus 1. And then we're going to subtract 4 to the k and then add 4 to the k in the middle. Because it's still the same expression, right? We're just kind of changing the way it looks. So this is still, notice this is a negative term, positive term. So technically these cancel out, right? So really we only have this and this. 4 to the k plus 1 minus 1. So it's still the original expression. We're not changing anything, we're just adding some elements. But it's still the same value overall. The reason we're doing this is because we want to try to factor out 4 to the k from the first part. So we're going to treat this as two separate things here. So I'm going to do 4 to the k. Now, if you think about it, if I factor out 4 to the k from 4 to the k plus 1, this is just one more 4. Right? So this would be 4 to the k times one more 4. Would give me 4 to the k plus 1. So here I would do 4. And then minus, and then 4 to the k, to get 4 to the k would be times minus 1. So it would be 4 minus 1. And that's for that orange part there, but with the 4k factored out. And the purpose of this was to get a 3 out of this somehow. And you can see here we get a 3. 4 minus 1 is 3. But bring down the rest because we still have that second part here. And then let me just simplify this real quick. So this is 4 to the k times 3. So this part is already divisible by 3 because there's a 3 in it, right? So no matter what k is, this number will always be divisible by 3 because there's a 3 being multiplied by that. So it's always going to be divisible by 3. So that part is proven, right? That part is, we've shown that that piece is divisible by 3, has a factor of 3 in it. Now what about this part, right? This 4 to the k minus 1. This, the way it looks here, doesn't really show that it's divisible by 3, except that we assumed earlier that 3 is a factor of 4 to the k minus 1, and that's exactly what we have here. And that's one of the big reasons we factored it the way we did. Once you have something that matches your assumption, this is automatically divisible by 3, because we assumed that to be true when we started this, right? We said, we assume that 3 is a factor of 4 to the k minus 1, and here we have 4 to the k minus 1, so this is automatically divisible by 3. So the proper way to write it is, this is divisible by 3 by our assumption. And that's the whole thing, right? That's the whole expression. Up here, we were not able to say that because, not by assumption, because this is not 4 to the k, right? This is 4 to the k plus 1. So that's why we still have to break it down.
The plus 1 that we factored out, it's just to the power of 1, right? So it just stays 4.
Plus 1, oh, you mean here?
Yeah, because it's like 4k plus 1. So we just have 4k, right? And just 1.
Yeah, so think of it this way. If we do, let me do this. Okay. If you have 4 times 4 times 4, this would be 4 to the third, right? And if you do 4 of them, that would be 4 to the fourth. So if you think of k as 3, then this would be k plus 1, for example. And yeah, if I take out, if I go from here to here, basically I have 1 less 4, right? So yeah, that 4 is here now. Any other questions on this one? All right. Let's try example 4. This one has an inequality in it. For all n's greater than or equal to 1. Prove that n is less than 2 to the n for any n greater than or equal to 1. The base case, if we let n equal 1, we will have 1 on the left and 2 to the 1 on the right. This would give us 1, and this is a question mark, right? 1 is less than 2 after computing it, and that is true. So the base case holds. That means we can do part 2, right? So we're going to assume that k is less than 2 to the k right off the bat, right? That's our assumption for this part 2. And then we're gonna show that k plus 1 is less than 2 to the k plus 1. So we're gonna assume that k is less than 2 to the k. But we need to show, and we can use that assumption, right? So using our assumption, we need to show that k plus 1, so that one is 1 bigger, and then the k in the power is also 1 bigger, is less than 2 to the k plus 1. So that's our setup, right? And then comes the induction step, like the hard part, right, to prove it. So we're going to have to kind of play with the exponent a little bit, similar to what we did in the other one. Let's say, let's do this in pink. Let's remember that an expression such as 2 to the n plus 1 is equal to, if I factor out a 2, then it's going to be 2 times 2 to the n. Does that part make sense too, right? So this is like 2 to the 1, right? 2 to the 1 times 2 to the n would be, you add the exponents. So it's just taking out a factor, one factor of 2, right? So instead of n plus 1, we would have n. And also remember that when you double something, it's like adding it twice, right? So 2 times 2 to the n is the same as 2 to the n plus 2 to the n. That's also an equivalent statement. Okay, so keep that in mind. Now let's see. We have 2 to the k plus 1, right? So we know that by what we wrote there, we know that we could write 2 to the k plus 1 as 2 to the k plus 2 to the k. So let's write that out here. 2 to the k plus 2 to the k. That's the same thing as 2 to the k plus 1. Now this is actually greater than 2 to the k plus 1 plus the number 1. Does this make sense why this might be true? So this was like as a 2 to the n plus 1, right? We were just kind of going through the exponent rules here as a review. So 2 to the n plus 1 is the same as 2 times 2 to the n. You can factor out 1, 2. And this is saying twice this, right? So twice this is this plus itself, right? Now, because of this, we know that 2 to the k plus 1 would be 2 to the k plus 2 to the k, right? That matches up with this property we're showing there. So 2 to the k plus 2 to the k, this kind of represents 2 to the k plus 1. We're saying this is greater than 2 to the k plus 1, right? So 2 to the k and this 2 to the k is the same. And then here, this is 2 to the k, but remember k is 1 or bigger, right? So this term would be a 2 or more, and we know that that's going to be bigger than 1 for sure. Does that make sense? So this number, whatever it may be, has to be bigger than this number, right? Just sort of instinctively. Now, we're saying this because we're going to say 2 to the k plus 1 is bigger than k plus 1. Okay? We know this by assumption, if anything else, because our assumption says 2 to the k is bigger than k, right? 2 to the k is bigger than k, so that's automatic, that's true now, in this whole part that we're doing. 2 to the k is bigger than k. 2 to the k is bigger than k, so if this is bigger than this, and I add 1 to both of these, then this is still going to be bigger than this. Does that make sense? Because 2 to the k is bigger than this. If I add 1 to both of them, then they're just both increasing by 1, but this number is still bigger, right, than this, because of this, our assumption. 2 to the k is larger than k. Let me write by assumption here. Okay, so it follows that let's start with 2 to the k plus 1. We know now that this is bigger than this. Right, so 2 to the k plus 1, which is the same as this, is bigger than this, right? So we already said that earlier, bigger than that. And we know that that is 2 to the k plus 1 is bigger than k plus 1. That's what we had. And we can flip this to kind of match the direction of the inequality. So this is saying that, let me highlight it here. Our original statement was n is less than 2 to the n. So our goal is to have n plus 1 is less than 2 to the n plus 1. Or k plus 1 is less than 2 to the k plus 1. Okay, and that's our proof, right, for that one next level. So this was the original one, and we're using k, right? But n is less than 2 to the n, so we wanted to get to k plus 1 is less than 2 to the k plus 1. So just based on those inequalities we did right now, that was enough to show that, right? So I just flip this around. So k plus 1 is less than 2 to the really the main trick here was factoring 2, well actually not factoring, but rewriting 2 to the k plus 1 as 2 to the k plus 2 to the k, so that we could compare it, this with this, right? And then this compared with this was by assumption, so that proved that this was bigger than this. And then from there, then it follows, right, that this is less than 2 to the k plus 1 1 2 3. Okay. All right, let's switch to sums of powers of integers and some of the formulas they have. For example, 7, let's see. Here are some formulas for adding up sums of powers of integers that you can use to compute certain sums. And let's do one of these. Example 7, B. I'll show you how we use these formulas here. 7b. So the sum here that we're doing is a summation from 1, index 1 to 4 of this expression. And not a difficult one, but it's just an example to show you how we would use those formulas for larger ones. This is only 4 terms, right? I is 1, stop at 4. So you can plug in 1, get that number, plug in 2, get that number, 3 and 4. So you're basically adding 4 terms, right? So not too hard to do it kind of by hand. But how do we do? But we want to use the formulas because sometimes this could be like 1 through 100 or 1 through 1,000. And then you don't want to write all that out, obviously. So first, let's see how we would break this sum down. So in the earlier section, they talked about when we first started seeing these sums, the properties of sums, these summations, and we can break these up. So in this case, I have this expression minus this expression. So I can actually break this up into 2 sums, and it's going to be one minus the other. So I'm going to break this up as the index will stay the same, 1 to 4 of 6i minus index 1 to 4 of 4i squared, like that. And then one of the other properties they gave us was that we could actually take out any constants that are factors of the expression, right? So this is 6 times 1, 6 is a factor, 4 is a factor. So let's take those out front. That would give me 6 times the summation 1 through 4 of I minus 4 times the summation of 1 through 4 of I squared. Okay, like that. And the reason we do this, and you'll get to practice this a lot when I do this. The reason we do this is because we want to get this to a form that we can plug in one of the formulas. For situations where we have more terms than this, right? So the first sum is for just I. So that's just going to be like 1 plus 2 plus 3 plus 4 plus 5, just counting numbers basically. The second summation is I squared, so that's going to be squared powers, right? So 1 squared plus 2 squared plus 3 squared plus 4 squared, and so on. So if you go back to the book, here you can see the formulas for those. So obviously you can see you'll have situations where you're adding powers of 4, powers of 5 also. But we're only doing these two right now, right? So this is the I. We could change that to this formula. N, of course, is how many terms you have, right? We started at 1, 2, 3, 4. We're going to have 4. So we could do this formula with n equals 4. And then we can do this formula for the second sum with n equals 4 as well. Does that make sense? So we'll plug those in. So for the first one, we do have 6 up front, right? Times. The first formula was n, which is 4, times n plus 1 over 2. And then the second one is the squared formula. That one's going to be n times n plus 1 times 2n plus 1 all over 6. But now we can just substitute these formulas in for these summations and just calculate this out instead. This will give us 6 times 4 times 5 over 2, so that's 20 over 2. Good. 10 minus 4 times, up here we have 2 times 4 plus 1, so it's going to be 9. This is a 5. So we have 5 times 4 is 20. 20 times 9 is 180. 180 divided by 6. Good. And this gives us 60 minus 120. So this that summation, original summation, will give us negative 60. Okay, so this is the reason you'll want to use those summation properties of breaking them up like this into 2 separate sums, taking out the factors, because you want to end up with these simpler sort of summations of powers, right? Sums of powers. And if you can get it to that level, then you can use these sums of powers formulas instead of sort of writing out all the terms and adding up all the numbers. Because these were easy, right? Only 4 terms, but there are some that have like 200 terms or 1,000 terms and so forth. So this is in the exercises. So remember, base case and then the extra term case. Let n equals 1. So on the left side, if we only want the first term, that's going to be a 2. So we're checking to see if 2 is equal to, and then plug in the n equals 1 into the formula on the far right. that would give us this. And 5 minus 1, of course, is 4. So we get 2 is equal to 2. So be careful because people get confused with the base case. They know they have to do it equals 1. So a lot of times they're going to put a 1 here. But remember, this is the first term, right? So come from here. So that's this side. And then, of course, over there, you plug in n equals 1. So be careful there, too, because once people use 2 here, they want to plug in 2 over there, right? So you're plugging in n equals 1. Remember that? 2 is equal to 2. So this works. We can move on to part 2 to prove it for the rest of the n's, not just the first one. So we will use k, right? So we're going to assume what they gave us is true, but we're going to write it with k's. Assume that 2 plus 7 plus 12 and so on plus 5k minus 3 plus one more term, so that's going to be 5 times k plus 1 minus 3. 5 actually, let me scroll here. It'll look too messy if I write it underneath. Is equal to the formula, right? The formula was n over 2 times 5n minus 1. So that's k over 2 times 5k minus 1. Plus the term that I added on the left, right? So I added this term. So I need to add it over here as well. Oh, I'm doing the second part already, huh? So let me do show that. Change this to show that. Equal to k. Okay, I just rewrote the original on top. So this is what we're assuming is true, what was given to us, and then we're going to show that it works for the next step, right? So the next step is, we said this stops at 5k minus 3, so the next term would be 5 times k plus 1 minus 3. And then now I'm adding this term to the left, so I have to add it to the right. Now we work on that right side, right? We work on that right side and see if we can get our goal. And more or less our goal is we want to go from k to k plus 1. So our goal would be k plus 1 over 2 times 5 times k plus 1 minus 1. So our goal is something equivalent to this. So we have k plus 2 times, should we put it over 2? No, let me do this first. 5k minus 1 plus, and this is going to be inside is 5k plus 5 minus 3. So that's going to become 5k plus 2. K plus 2. Okay. What else can we do? Uh, 5k. Oh, this one? Yeah. Okay, yeah. Multiply that out. We would get 5k squared minus k. This will be over 2, right? Plus 5k plus 2. Okay. If I add these together, I would need a factor of 2 on the other side, right? So let's say I put a 2, make sure you use parentheses here, and then a 2 on the bottom like that, just so I can add these together, and then we'll keep simplifying. This is 5k squared minus k plus 2 times 5k plus 2. This is all over 2 now. I get 5k squared minus k plus 10k plus 4 all over 2, which simplifies to 5k squared plus 9k plus 4. This is all over 2. Okay, so now what we can try here is let's work on the goal. Let's multiply this out, and then we get an expression that looks like this, and we'll know that we got the right thing, right? So if I do this, if I work on the goal, let me work on the inside first of that bracket. So this is k plus 1 over 2. Inside here we have 5k plus 5 minus 1, which is k plus 1 over 2 times 5k plus 4. Okay, and if I multiply this out, I'm gonna FOIL on top, right? FOIL on top, we get k times 5k, k times 4 plus 4k, 1 times 5k, 1 times 4. And then simplifying a bit, 5k squared plus 9k plus 4 all over 2. And that works out for us. Okay, good.